Welcome to AP Podcast 6.1. This is the start of our thermodynamics unit. It's going to be a whopper, so hold on. It's going to be a little bit of review and quite a bit of new stuff. So let's first talk about the nature of energy. And if you recall from your previous days in chemistry, the ability to work or produce heat is what our definition is of energy. Now, to do work is mostly a physics thing, although we'll be talking about work today. But producing heat, that is definitely something we see in chemistry all the time because we're doing reactions and they are often exothermic. So here's a few things about energy that you already know. You know, one, that energy is conserved. Okay, we can transfer it from one form to another, but we can't create it or destroy it. I'm going to introduce you to a term of work today, and work is simply just a force acting over a distance. I'll get back to that in just a second. The other types of energy that we're used to seeing quite a bit are potential energy and kinetic energy. Potential energy is due to position. If you're in physics, you know about they always talk about a rock sitting on a top of a hill that could roll down. But for us in chemistry, it's typically about the composition. And that composition is usually the chemical composition that can end up creating heat. And then kinetic energy, due to the motion of the objects. Again, there's a lot of overlap with physics. For us, when we talk about the motion of the objects, we're usually talking about molecules or atoms moving, all right? And so here's a formula you've seen before. Kinetic energy equals 1/2 the mass times the velocity. And again, it doesn't really play a big role in AP about for calculation purposes, but it is a very important concept, and those of you in physics or to be in physics will use it quite a bit. So let's move on to the next thing in energy, and that's heat and temperature. It's important that you can keep the difference straight in your brain. Temperature is the measure of the particles, and those particles moving around. If you think about, you've got this beaker, you got all these particles moving around. We stick our thermometer in there, and it goes to a line, and we read it, and it says 40 degrees Celsius. All right, the thermometer is measuring these particles moving around. All right. Now, you've not heard of a heatometer or heatometer or whatever, because heat is just a measure of the energy in something. And the way we measure heat is we have one object, we put some energy into it, and then we often will put it into some water, measure the temperature change of the water, and we can calculate the energy, because energy is this thing that is transferred between objects. So we'll talk about energy as this substance being transferred, whereas temperature is the motion of the particles. So real important that you keep those things straight. Now, when we're looking at what we're measuring, we often talk about the surroundings and the system. Okay? The system is what we're looking at. For us, often in AP, it's some kind of beaker or flask. And then the surroundings is everything else. It would be the air around the flask, that kind of thing. And so we're going to use system and surrounding quite a bit. And you remember that the system is whatever part we're looking at. That's the important thing. Here's two terms that we know of from the past. Exothermic reactions release energy to the surroundings. So imagine you've got a beaker, and we do some magic, and then it's given off energy. Okay, it's given off energy to this area out here, and this area out here is the surroundings, right? Then an endothermic reaction, and if you guys remember the frozen board demo, I had a board there, did some magic here, and then the board was frozen. Okay, the energy out here, okay, all that energy went into our system, and so since energy came into the system, it was an endothermic reaction because the system absorbed the energy. How's that? Making sense? Let's move on to the next thing. So I've got a couple visuals, and if you can see a reaction here, notice one of the products. Product here is heat. Okay, that means heat is given off, right? And that's what this shows. So here's our potential energy. We've got these chemicals up here, and they've got a potential energy, and then we do a reaction, and this is just a good old combustion reaction, and the products are here at a lower energy state. Well, the difference there is the heat that's given off in the reaction. And of course, if you're burning methane, you're going to feel some heat. And so this difference right here, from here to here, that's the amount of energy that's given off. On the opposite end of that would be a endothermic reaction. You've got a couple reactants right here, some nitrogen and oxygen. All right, pretty stable things. Heat them up, and it causes them to react and make some NO. Now, NO is at a higher potential energy state than nitrogen and oxygen, and so this is an endothermic reaction. You had to add energy to those two molecules to make some NO. So that's an endothermic reaction. So when we look at thermodynamics and heat, we've got to keep track of all the little symbols and signs and things like that. So I've got a slide here. Let's look at this. Thinking about the direction of the energy. Okay, every energy measurement has three parts. A unit, okay, which of course you guys hear me harp on all the time. Now for us, for the most part, it's going to be joules, but it might be calories. And if we think about, Americans and the food we eat, it's capital C calories, which is a kilocalorie. But for the most part, the world uses joules, all right? And then besides the unit, of course, you need a quantity. How many joules? Let's say, for example, something like 500 joules of energy. And then the last thing, and this is really important in thermodynamics, and sometimes this really causes some confusion, is a sign to tell the direction. Okay? And the sign is going to be negative if it's exothermic and positive if it's endothermic. Now, that might seem a little weird to you because exothermic energy is given off. But again, let's think about how we define things. Here's our system, and here's the surroundings out here. Okay? If I'm looking from the system's perspective and energy left me, right, as in an exothermic reaction, energy left, okay, from the system's point of view, it has less energy than it used to. Okay, so now we've got a negative value. Now, if I take the surroundings and I take some energy and I add it to the system, well, the system has gained energy, and so an endothermic reaction gives us a positive sign. Right? Really important that you keep those things straight because we're going to look at that quite a bit. Now, I got a couple visuals here for those of you who like pictures like me. So here's my system. Energy goes out. The energy of the system is less than 1, right? It's going to be negative. And then, of course, the other diagram is that if energy is going into the system has gained energy, and therefore it becomes positive.